Hello and welcome. This is Chapter 13, Section 1, on a little history of Newton's theory of gravity. And it's certainly a section that you can read. It's a history section. I certainly want to add a little bit more to put even this historical perspective into perspective. This chapter is one of the second in our application type chapters. And so it's going to be picking and choosing lots of topics from previous chapters. Force, it uses energy, circular motion makes a comeback, obviously. We even introduced some elliptical orbits, and to that we need to revisit the concept of angular momentum, potential energy, kinetic energy. A lot of it is all here, even work in some sense. So, and we're of course trying to understand the motion of stars in galaxies. Of course, the understanding our universe is far beyond what this chapter can cover. Newton's theory of gravity pretty accurately describes taking a shuttle to the moon. In some sense, it very nearly describes our attempts to go to Mars. And when you get closer to the sun, it is about 99.9% correct. But once you get really close to the sun, once you get close to the center of the galaxy, then Newton's theory of gravity actually starts to be less and less accurate and more of an approximation to more general theory that we don't touch on, called Einstein's theory of general relativity. Your instructors will certainly have plenty more to say if you ask those interesting questions. But this is still a very good topic to understand because satellites, GPS satellites, any sort of telecommunication satellites, the space station, any things orbiting the Earth certainly follow these principles. Okay, so the first section is about a little history. And before I jump into these observations or these results, I want us to just quickly understand what's going on and how this fits in, because gravity, almost more than any topic in physics, really underscores the fact that this is an empirical physics. Like every science is always just observations based on what you physically observe. And what do you physically observe in the night sky? If you're going to make this very elegant, beautiful theory about how stars and planets orbit around each other, it all comes from observation. So what do we observe in the night sky? Well, for centuries, millennia, there was a fixed, if you look in the night sky, you go out, far away in the country or something, or on a clear night, you'll see more or less a fixed bunch of stars that are all rotating more or less the same rate. And we might have, in ages past, we might have called that the heavens. So obviously the sun and the moon are going around in their paths, but then there are these so-called five wanderers. The Greeks called them wanderers. That's where we get our word for planet. Planetos is a Greek word, meaning wanderers. And the wanderers in the night sky would take this sort of path. It would be a path something like this. Okay, I'm going to draw it now. Something like this. In the night sky, you'd see the planets, and they'd take, over the course of several weeks or perhaps months, they would take this sort of path in the night sky. Something like that. All right, so all the other stars from which we get the constellations and which we get all the other objects, they more or less move in a fixed location in a circle around each other, right? They're all moving around the Earth, and they're all about the same, more or less, angular distance away from each other. So it's basically like the same, if you imagine like a painting of stars constantly just rotating in the sky, that's what most of the stars do. And of course, like I said, you have the sun and the moon, but then you have these wanderers. The Greeks understood that they analyzed five wanderers. And if you look up on this, look up at this first PowerPoint, you see, or the first bullet, you see Mercury, Venus, Mars, Jupiter, and Saturn. Those were the 5 wanderers, and they had these weird trajectories. And so way, way, way before Newton and before Kepler, in the classical age, you had someone called Ptolemy. And it's really interesting because Ptolemy, way before Copernicus, the Earth was believed to be the center of the universe. Because what do you observe? You observe all the stars, everything in the sky moving around the Earth. And so what they established is that these wanderers and the moon and the sun all have their own sphere in which they orbit. And what are they made of, by the way? It was believed in ancient times that you have the 4 basic elements on Earth: earth, fire, air, and water, right? The 4 basic elements. And it was believed that the objects outside of the planets or outside of Earth in the celestial bodies were made of a quintessence. That's Q-I-N-T, essence, the 5th element, if you want to call it that. And so Ptolemy said, to describe the pattern of these wanderers, we're going to say that the Earth is at the center, and these wanderers orbit in a circle around the Earth, but in addition to orbiting in a circle, they're moving in their own little circle. Okay, so it's the planet, say, Venus, right? So what Ptolemy described is that Venus, much like all the other Mercury, Mars, Jupiter, and Saturn, they're moving in the circle, but that circle is also moving, that circle is also moving in this orbit. And so that's what they described. And if you get the rotations right, if you get the rotation of Venus, or in this little circle with the rotation of the big circle right, you can more or less produce this sort of pattern that's observed on the Earth. And it was observed to be correct to more or less 1 or 2% degrees of accuracy. So this was a model that was valid for many centuries, and it described the motion of these wanderers. And 1 to 2%, anyone will tell you these days, especially in astrophysics, is excellent. Modern measurements in astrophysics are more like order of magnitude, not necessarily percent-wise. So this was the prevailing centuries before Kepler. And so the Renaissance happens and other things happen, and they start to think about different things. Copernicus suggests that maybe Earth isn't the center, but that the sun happens to be the center. And then these observations happen. So Tycho Brahe now, in this slide, they connect the dots. And so his Johannes Kepler was his assistant, and he pored over this data. So Tycho Brahe took all this astronomical data, an aristocrat, he had all this data. And so Kepler took 40 years pouring through all these tables and tables of data. Very impressive, something that if you took Tycho Brahe's data now and analyzed it with a computer, it would probably take, at the very most, maybe microseconds, milliseconds. But that's how they did it. So Kepler poured through all this data, and he was able to show that if the sun is the center of these other wandering objects, then there are these 3 laws. So that's a little bit background. So these 3 laws, which we'll certainly get to in the course of this chapter, but the first one is that all these wanderers, including Earth, actually, orbit the sun in an elliptical orbit with the sun at a single part of the focus, or a single foci, right? An ellipse is like a circle, or a circle is like an ellipse with the foci aligned at the same spot. And a quick way to make an ellipse is to take 2 push pins, stick a piece of paper on a bulletin board with 2 push pins and connect a rubber band between them, and keep a constant tension, and that constant tension, the rubber bands will make a perfect ellipse, depending on the size of the foci, depending on the tension of the rubber band. But that's the first law. Second law is what we call equal areas and equal times. So obviously, the closer to the sun the wanderer gets, the faster it's moving. It certainly says so right here, faster. The further away from the planet the sun it gets, the slower you're moving. The thing, although the velocity changes, although the angle between the velocity and the radius changes, because it's an ellipse, the thing that stays the same is the area. The area stays the same. So if this was like an elliptical pizza, then these two pizza slices would have the same amount of pizza in them, right? In equal times. So if you cut up the pizza into equal time slices, then those would all be the same. So that's the second law. Sometimes this follows from conservation of angular momentum, actually, something that we'll derive in the last section. And then the third law is the planets aligning, right? How do you align all the planets with the data of their periods, their orbital periods, like a Jovian year or a Martian year or Venusian year. There's a law that relates the square of the period to the cube of the radius. And it looks like this is a log plot, and those are helpful in science and engineering, where rather than just graphing the absolute values, you graph the powers. You graph it with the powers of 10, and you usually get, if these two values are related by a straight line, or if these two values in the x and y coordinates are related by a power, then the slope of this line will be the power. And certainly enough, yeah, they get this expression, and that 1.5 is the slope. That's 3 halves. So that means if it's 3 halves, that means that as one increases as the square, the other increases as the cube. And that's certainly the relationship of Kepler's third law. So those were the mathematical results that Kepler had established experimentally. Okay, it all goes back to Tycho Brahe's observations, Kepler taking the observations and putting mathematics to it. Then finally you get to, well, before we just quickly get to that expression that circle is a special case of an ellipse, after the observation, after the mathematical description, then you get to the why. And Isaac Newton is the one that came up with the why. So it was Isaac Newton who's credited with the physical formulation of why the motion of the wanderers is described mathematically the way Kepler says it was, from the observations that Tycho Brahe made. And certainly he had talked about, well, is the moon falling towards the Earth? Because where does the moon fit in all this? Does the moon orbit the sun as well? Kind of, but it orbits the Earth too. And so what he did is he was able to use basic circular motion. This is in the textbook, and you're more or less expected to go through this derivation, but he was able to find the free fall constant of the moon falling towards the Earth. And it's certainly not 9.8. The upshot is that the ratio of the acceleration due to free fall of the moon towards the Earth and say exactly on the Earth is in strikingly curious relation to their distances. So you take an object near the surface of the Earth, right? It has an acceleration due to free fall of 9.8, right? Meters per second squared. If you take the ratio of those, if you take the ratio of the free fall on the Earth, let's just say G at the moon divided by G on the Earth. Now keep in mind, this is not the gravitational pull of objects towards the moon. That's about 1/6 that of the Earth on the surface of gravity. This top G is the free fall constant of the entire moon towards the Earth. If you take the ratio of those, it ends up being nearly exactly the ratio of the distance of the r to the moon to the Earth divided by the radius of the Earth. Flip that around real quick. The radius of the Earth and the distance from the Earth to the moon squared. that's the key idea that Newton was able to justify to find a free fall constant of the moon. So you take the distance of the Earth, that's, the book calls that capital R. All capital R is always radius in this chapter. And then the other quantity being the, the other quantity being the little r sub m. Little r is distances, okay? The square of this ratio of r sub e to r sub m is equal to the ratio of those g's, because this is 9.8. This is like 0.03, something like that, 0.003, really small number, but those two are more or less equal. And so from that, if we know the free fall constant on Earth, then we can show that, manipulate this equation a little bit, we can show that the acceleration due to free fall, so little g as a function of r, it's going to be something like this. It's going to, it depends on the radius of the Earth. It depends on g at the Earth, but it ultimately is 1 over r squared. It's an inverse square law, and that is the resulting theory of Newton's theory of gravity. So in the next video, we'll formally state Newton's theory of gravity and talk about some examples. Really, it's a force law that there's different practice problems, different estimates. Eventually, we want to get to energy. So thanks for watching, and we'll see you back here for the next video. Take care.